Good afternoon. My name is Joshua Harris, and this is my project number 6, and it is revolving around solving the longest path problem by implementing a hybrid algorithm of a genetic algorithm along with the wisdom of crowds approach. Now, as a quick introduction, in this project, our goal was to implement a genetic algorithm with a wisdoms of crowds algorithm to attempt to solve an NP complete problem, of which I chose the longest path problem. Now, we needed to choose an approach to an NP complete problem and use this algorithm to successfully find a better solution after each new generation that we do propagate. Now, the problem of finding the longest path is in a generic undirected graph, that is, where G and V is the set of n vertices and E is the set of m edges. The goal is to find for all of the vertices U, V that are in V, the longest path from U to V using weighted edges. And in our example, we're going to be using the Euclidean distance between those two vertices A and B, and that is going to be considered our weight. Now we consider simple paths those that do not have any repeated edges or vertices. And we can tell that this problem belongs to the NP-complete class of problems, as it is a generalization of the Hamiltonian path problem and cannot be solved in polynomial time unless P is equal to MP. Now first, I would like to discuss my approach, and we'll start with my comparison algorithm, which was just an unaltered genetic algorithm. Now I started this project with the implementation that was very similar to our previous projects, and I start with my base genetic algorithm that takes our input from a file that has those X and Y coordinates attached to each of them. And then next it needs a starting population. So I run through the file, creates my comparison parents, and then once I do that, I take a copy of the array and then I begin shuffling through that a number of times to get good variation for that initial parent. And obviously, as this was a different problem from our previous approaches with the TSP problem, the very first thing I needed to work out was, or before I started doing my complete shuffle, obviously with the TSP I wanted to retain those first vertices, that way I could always add it in later as my return city, but I've removed that and now it doesn't contain that cycle. So after the first population of X vertices is created, I begin running my genetic algorithm. I start by capturing the total distance of each path and mapping it to each object. Now while doing this, I make sure to capture my maximum and minimum of each one of those in the of the entire population, because I use that later on for normalizing the fitness levels and as well as displaying that best overall performer through each successive generation. And once I have that fitness data, I run this choosing algorithm, and what this does is it will allow me to select the two parents that I'm going to use in the crossover algorithm that will create the offspring that's going to be the base for the next generation. Now once that is chosen and I run it through my crossover algorithm, it will have that newly created child, and that is going to be again the base for the new population. Now for my hybrid algorithm that I actually run many of my experiments off of utilizes many of those same features that we saw or we will see in my genetic algorithm, but instead of using that crossover to create the new child as well as the picking algorithm, I utilize a wisdom of crowds approach. Now what this is going to do initially is it's going to take the top performing 50% of those individuals, we'll call them experts in this position, And what I do is I select of each one of those individuals for each position. I choose the most chosen city for each one of them. That is to say, if 12 of my experts chose city 7 as the start point, that is going to be the start position for the newly created child. And I would do this for each continuing generation. Now, to get a better idea of how I implemented my solution for this problem, I'd like to do just a quick demonstration of how my algorithm works. So as we can see, this is my GUI here. Right now it is set up to run with my wisdom of crowds algorithm. We will see in just a second how this works. So right now we're looking at a total of 77 cities with a population size of 100. And you can slowly see that grow over time and try to create the longest path that it currently can. And as opposed to my genetic algorithm here, we can see that it does stagnate towards the back end here, but overall still gives us a pretty decent example. Now down here at the bottom, you can see how I approach my wisdom of crowds algorithm. What I do is I initially take the top performers of the previous generation, select the top 50% that are over the 0.1 mark, and then from them, again, as I previously mentioned, I do select each of the cities in order which was selected the most by my experts. Now as we jump back here, let's take a look at some of the results from my experiment. Now, the very first thing that we're seeing on the screen here are just the average distances for both the genetic algorithm and the wisdom of crowds approach. This was done over 10 successive generations. And if we take a look on the left, we see that, hey, they have a pretty much the same growth over time. If we take just a quick peek, we see that there is initially a little bit less variance with the population distances chosen in the genetic algorithm. They do slowly kind of come together over time, as well as reaching a pretty decent answer for our longest path as well. As compared to our wisdom of crowds approach, we do see that the variance is a little bit lower. We have fewer outliers here in my wisdom of crowds approach on this specific approach to the problem. Now, the next set of experiments I did was a result of the distance for each population as time elapsed. Now from here you can see, if we take a look at our genetic algorithm here, that with the genetic algorithm, it continues to have pretty high variance through each successive generation, with it slowly kind of coagulating a little bit over time as we do reach some of those end populations. As compared to the wisdom of crowds approach here, we can see that with the start population there is some pretty high variance, but after that first generation, many of those individuals in the population do come together with the same results with just a few outliers. Now we can obviously see that the average of those guesses is typically higher than any one performer within the entire generation here, as we can see that we have more outliers below our average guess rather than above it. which was kind of what we expected to see with that wisdom of crowds approach. And if we also take a look at just the averages overall, we can tell that the end result is about the same as with our genetic algorithm. Now, there are a few additional experiments that are still in the works here. If we take a look, that's my first set of experiments. I wanted to adjust the chosen experts. So what I initially did was with my top 50% performers in each generation being considered as my experts, but with a few more experiments that I am doing, whether that be choosing the bottom 50% as my experts, as well as possibly taking a split between the best performers and the worst performers and averaging them out and seeing whether or not that's my general approach or the child based off of uh, these two sets of experts would be generally higher than any one performer in the actual population. And then the last set of experiments that I am working on is starting with just a very efficient, low cost path and seeing if I get any deviation with my results and its progress with both, not just the genetic algorithm, but with my wisdom of crowds approach as well. And lastly, here's the references that I initially utilized with just my initial set of experimentations. And that is my presentation for my project results. Thank you for your time.